actually organizing this event for my first visit here to Alabama. Quite exciting. So I'll be trying to introduce, and also especially with a view to the students, so how to do some actual computations in anti-de Sitter spacetimes. I believe yesterday, day before yesterday, you have learned a little bit about what AdS-CFT is, so that you can use some gravitational computation to learn something about strongly interacting quantum field theories. And so this lecture will be really focused to how to do one practical computation, which will be one of the problem sessions in this kind of AdS spacetime, a simple one. But of course I also want to motivate a little bit why we do this and what is the idea behind it. And I always like to point out to this kind of what is my artist impression. It's probably more of an impression than real art. But so what the idea is here, you have, for instance, I'm mostly focusing on heavy ion collisions. So you have two of these lead nuclei or gold nuclei that collide at super high velocities. And in this case, they collide not exactly head-on, but a little bit off-central. So you see that this part of the nucleus collides, and the rest just flies on. And what happens in the middle, there is so much energy that there is this, all the quarks and gluons, they basically form a quark-gluon plasma. And it's actually somewhat interesting from this picture, you can already see how we more or less know this. Because of this, they don't collide exactly head-on, so they collide slightly off-central, and this creates like an elliptical shape of this plasma. And you could expect this is something very violent, you just have particles all over the place, and it would be somewhat boring. It would be just particles all over the place in your detector, in LHC or RIC in Brookhaven. But it's not what we find, and we don't find this because it's, at least that's the current model, it's a strongly interacting liquid, basically. And because it's a liquid, you have some pressure gradient, which is much larger in the short axis than in the large axis. Because there's a lot of pressure here, so it pulls stronger in the short axis. So what you will find is you'll have a large push in this direction, and you'll find more particles over here and over there, which is larger arrows here, than particles up there. And this is what we actually find in these LHC experiments, or previously in Brookhaven. And that's how we more or less actually know that this interaction is strongly interacting, otherwise you would never find that. And this is also what motivates us to study this using AdS-CFT, because if you have a strongly interacting QCD kind of plasma, well, you cannot rely on perturbation theory, so at least you have to do some kind of strong coupling computation. We cannot, well, I think yesterday it's already been stressed, we cannot really do a QCD computation, but we can learn something new, perhaps using these AdS type computations. And this is what this picture is supposed to mean. We have this nucleus here, quark-gluon plasma, and it might be strongly interacting. But then there's this extra direction, it's called holography. And this extra direction is supposed to be more or less the energy scale. And what you will find, and what we'll try to do actually, is to collide something in this AdS, make a collision, and see how then in this AdS actually black hole will form in this extra direction, where this, well, so if you go down, you go to lower and lower energies, and at some point you reach like the energy scale of the temperature, and that will be the temperature of the black hole. And beyond that, there is this, there's the black hole, of course, the black hole horizon. This kind of cuts off thermal physics, and this black hole horizon, I think probably Crystal introduced it yesterday, will behave more or less like a fluid. But the crucial thing, at least in this lecture, is that we want to model the thermalization. So basically, these nuclei collide. There will be some quark-gluon plasma, but it will take a while before this quark-gluon plasma actually forms. I mean, it doesn't instantaneously thermalize, it takes a while. And this, we think, could be related to this, the time it takes for this black hole to form and also be described by this fluid dynamics, which will be there in some time, but this is kind of what we want to compute. So ideally, of course, you just put like a nucleus like this with all kinds of protons, neutrons, and you try to collide something in AdS, but that will be very, very complicated, and nobody has done this to full extent. But in the exercise class, you actually do a homogeneous kind of simplified approach, where you really have something which is not described by fluid dynamics, and then you see that because of this black hole, the gravitational dynamics, it will go to a fluid, and this is then thermalization, and the time it takes before it becomes a fluid will perhaps teach us something about the thermalization of heavy ions. So that's what's in this picture. And how will I try to? So yeah, I didn't prepare too much material, so please interrupt at any time if it's supposed to be very clear, but it's not supposed to be very long. Well, so interrupt me, especially for the students. So, okay. Okay, so I'll start with this. I introduced a little bit dynamical black hole formation. So what will be essential in this, at least in our approach, well, Hans in the audience does actually Einstein. You have to solve Einstein equations, and there are basically two approaches in the current setup in the community. Hans is doing one approach, and this is the approach, the characteristic formulation, which is basically other coordinates, and I'll introduce this, and it has some advantages and disadvantages. But the advantage is that it's actually rather easy to do some simple computations. So AdS-CFT is already covered in the other lectures. I just wanted for this, with a view to apply AdS-CFT to heavy ion physics, to stress 2 points. Which probably has been mentioned already, but in AdS-CFT you always have to assume that the coupling constant, which is basically the 't Hooft coupling constant in QCD, which is lambda is g squared times the number of colors, so that is the effective coupling of QCD. You always do an expansion where this coupling is assumed to be infinite, and then perhaps you can include like 1 over lambda squared corrections to that. But there's always this. Yeah, so just like in perturbation theory, you expand always in small couplings, like g squared, g cubed, we're doing all the loop diagrams and all that. AdS-CFT does it the other way around, and you expand from strong coupling to 1 over lambda squared, smaller couplings. And of course then the question is, do we want to apply AdS-CFT to QCD? Well, only if the coupling is large enough, and in QCD actually the coupling is not infinite, which is the leading order term. So all these computations I'm presenting, or most people do, are always at lambda equals infinity. So we always have to worry about if these computations are really close to QCD and how much we actually learn by applying this kind of picture to QCD. And in my flash of recent research, which I'll try to end with, I'll show you actually some actual computations which perhaps suggest that, we might be doing quite well using AdS-CFT, and we can learn a lot, but that there are definitely differences with QCD. And at least my current guess is that the main reason why we don't really reproduce the QCD results spot on, you wouldn't expect this, but the main reason is probably this large coupling expansion. Because as you know, QCD is asymptotically free theory. So if you go to higher and higher energies, the coupling goes down and down and down, and at asymptotically high energies, the coupling goes to 0. So there, really, what you should be doing is perturbative QCD. But this coupling goes down very slowly. It goes down actually logarithmically with the energy. So in the regime where we're interested in, the coupling is really not 0 because it goes down so slowly, but it's also not infinite, of course. So there's probably some intermediate regime, and probably one should try both. One should do like from large coupling and from small coupling. From intermediate coupling, obviously, is very hard. And well, the other point is that even if perhaps the actual computations don't work out quantitatively, like very precisely, you can of course still learn many qualitative lessons. I think this is one of the biggest successes perhaps of this whole holography, applied holography. Even in condensed matter, I think Matthias introduced it, perhaps non-Fermi-like surfaces or holographic superconductors, all kinds of very qualitatively different dynamics taking place in this kind of evolutions, which can be very different from the perturbative framework, and that just gives you some idea about the possibilities by just doing these computations. And well, what I'll actually do in my recent research, I tend to do this comparison a little bit more quantitative, so really try to put in the numbers and see what we get out. And I think we can also learn something about that, because then, of course, even if it doesn't really work, then you know at least how bad were all these approximations you need to make when using AdS-CFT. And along the road, as I hope previous people have already convinced you, learned a lot of cool physics about black holes and how these things form. Good, so, well, as you probably already guessed more or less from this previous picture, I mean, if you want to do a collision like this is Einstein equations, so highly nonlinear coupled partial differential equations. So usually pretty difficult to solve even numerically, but analytically, there's little progress you can make usually. There are good exceptions, of course, but in this talk we'll focus on numerical methods to solve the Einstein equations, and then actually if you have enough symmetry, this is actually not so hard, and I think you can do this in an afternoon, which we'll try to do perhaps this afternoon. I always use, at least for myself, Mathematica, which is nice because you just put Einstein equations in. It's easy to change these equations, and then Mathematica is actually quite good in handling numerical problems like this, even though you usually have to work a little bit harder than just trying to put it in ND solves. But I'll try to give you one example of what we always use in this characteristic formulation. Well, we is me and different people who actually started using these kind of formulations, like Paul Chesler. We always use spectral methods to solve these ordinary differential equations, and I'll try to introduce that a little bit because I think it's very useful to, well, for this kind of problems with spectral methods, it's just a very general tool to very efficiently solve ordinary differential equations. So even if you don't want to apply it to black hole formation, you can apply it to basically any type of differential equation. And then of course I'll try to end with some view of what we're currently doing. And I wanted to promote a little bit, if you are interested in doing more things, on my website I put a few of these kind of example notebooks, for instance in Mathematica, which go a little bit more in depth if you want to really learn these kind of things. For instance, the spectral methods I do non-linearly, whereas here in the lectures I'll focus on the linear problem, etc. Yes?
Regarding differences between n equals 4 and the holographic limits in QCD, are you going to say anything about large n?
Yeah, no, but I can do it now. Yeah, since you asked. So indeed, so I wanted to stress these 2 points because I thought this was in my view, this one is the most important caveat of using AdS-CFD. And the reason the large n I'm not so worried about is a plot which is from the lattice QCD community, in fact, because they can of course do all kinds of thermodynamic computations of QCD, and they did it for SU3, which is normal QCD with 3 colors. But they also do it for SU4, SU5, SU6. And then they look, for instance, at how the pressures go as a function of the temperature, energy as a function of temperature, all thermodynamical quantities, and they can accurately compute that. And what they see is that if you're at NC equals 3, and you go to NC equals 6, then you're exactly already at the large n limit. These curves all go spot on. All the pressures are, you just get a trivial Boltzmann factor just by rescaling of n. So at least for thermodynamics, this large n limit seems to be really fine. And then of course it's a little bit of a leap of faith that it's AdS-CFD, which does all kinds of time dependence phenomena. Then perhaps there are other quantities where this large n limit is not so good. I don't know if you are thinking about specific examples.
Yes. Well, I mean that this was the reason. I mean, the shear viscosity story was novel and remarkable when people first realized it for precisely this reason, that n equals 4 has very similar thermodynamics as, you know, QCD and the large n limit, but the time-dependent physics is completely different. Shear viscosity is governed, you know, governed by mean free path in large n QCD, whereas in AdS-CFD it's set by temperature. It's a very small viscosity. Anyway, the statement that
I thought people have actually computed the shear viscosity, well, famous is of course 1 over 4 pi and large coupling limit, but I think there's a 1 over n corrected version where the difference is in fact not that big, like 10%, maybe 20 at most.
But in QCD it's very different. You don't see this from the thermodynamics is a wonderful thing.
No, but I don't see what you mean. How can you compute in QCD? In QCD this has not been computed. The shear viscosity has strong coupling. Nobody has computed.
That's right.
Even at large n.
The weak coupling.
Okay, so maybe. So you're saying that at weak coupling the large n limit behaves differently. Well, okay, so but that I maybe not know, but I mean at strong coupling I'm pretty
qualitatively different phenomena in AdS when you take finite n. Black holes are not black in finite n, things like this.
Yeah, but people more or less understand this because if you, so 1 over n corrections correspond to quantum corrections in the bulk, so you can actually, there have been computations doing these corrections, so you get some Hawking radiation, which is actually physics which is fairly well understood. Because I think this shear viscosity is actually a good example because it's not purely thermodynamic, it actually has some dynamics. And okay, if you compute the correction, it's 10-20%, which is where I think this one is actually worse. But well, I don't know if other people have something to say about it. But there are of course other differences between. Okay, so I should say this a little bit. So AdS-CFD, we usually work in NS4 super-Young-Mills, which is highly supersymmetric and it's simplest to do AdS-CFD. But it's a very supersymmetric theory, and QCD actually. So you could worry about this, that these theories are super different. Why would we study anything in a super different theory than we're really interested in? And one way I think about it is that, okay, probably if you collide 2 lumps of energy, what we're basically doing, instead of colliding 2 nuclei, in completely different theories, it's probably quite a different initial state, for instance. But then I'm kind of, I think, lucky in the problem we're studying, because we're really interested in what is this thermalized plasma in the middle formed after this collision. So perhaps if you have like two theories which have a somewhat different field content, perhaps after thermalization it just becomes a thermal state. So you could definitely hope that, okay, the thermal state is different because of a different field content, but perhaps things like the time it forms, or actually I'm also interested in like what is the fluid profile, what is the energy density profile. Perhaps that's not so different because it's governed by strongly interacting physics, or alternatively governed by gravitational physics. One other way to say that is that if you look at the very low, at the low energy behavior, say the initial conditions of a nucleus at rest, probably very different in QCD and explosive young males. But I think that this difference is mostly in energy scales which are much lower than the temperature formed of this plasma. This is formed at temperature like 600 to 800 MeVs perhaps, so very rather high energy. And all the differences between QCD and explosive young males are really largest by, for instance, the deconfinement temperature of QCD, like 170 MeV. And this dynamics will be behind the black hole horizon. So this kind of gravitational collisions and this kind of, the formation of this black hole has some kind of universality, which is also in shear viscosity. If you compare very different theories, always same answer. And part of the reason is that all the details of the theory might be behind the black hole horizon. But this is perhaps a little bit more of a hope than I can make very precise. Any other questions? Yes.
So I understand that when thermalizing, what plays a huge role is the fixed point structure of the theory. So what people found, I think also, I'm not an expert, but I think in the quark-gluon plasma are these pre-thermalized phases, where the interpretation is that while dissipating the energy, the system passes very close to fixed points, of getting into it, but it's getting close by, which slows down the thermalizing dynamics. So it looks kind of thermal, but it's not really. So I was wondering, since we're saying QCD, I mean, obviously it's asymptotically free, and equals 4 is just conformal, if that might be, have people thought about this? Like, what
so this is a very good question. Okay, so one simple comment about the last statement, that indeed QCD is not conformal, has this running coupling and all that, and it's supposed to be need conformal theory, completely scale invariant. But in the regime, again, where we're interested in, like the 600, 800 MeV, this dependence on scale in QCD is fairly small.
Yeah.
I mean, of course, if you want to apply ADCFT at 150 MeV, you're completely wrong. But perhaps for this initial thermalization, this conformal theory is not so bad. And also, of course, you probably know that in ADS-CFT you can improve on this. You can study different ADS theories which are not scale invariant if you're worried about this.
Are there examples what you just said? Like you're completely wrong? I don't remember that.
Like at the deconfinement transition, I mean, in anisotropy males this is simply not there. Right? But there are examples of theories which would have fairly similar dynamics.
Yeah.
I mean, not exactly at QCD.
Yeah.
To come back to this pre-thermalization phase and this non-thermal fixed point, it's a little bit hard to answer because this comes from the perturbative QCD community. So what they always do, they do real perturbative QCD, and what they actually do is they take a limit where there's so much stuff that they can actually just solve classical Young-Mills equations. QCD, of course, the glue ones are governed by Young-Mills equations. They solve these equations numerically, so it's also challenging actually. And then indeed they find this non-thermal fixed point where there's some non-trivial scaling behavior, and then they guess. I mean, they run into a non-perturbative regime, and they cannot compute further, but they guess that after the non-perturbative regime you go to a thermalized phase. As far as I'm aware, we just don't have this strong coupling. So we don't have this non-thermal fixed point. We always just, you have some collision, and basically because of gravity you form a black hole, almost I would say as fast as possible. We will see this a little bit in the ADS-CFT. So I think it is really different dynamics from weak coupling and strong coupling.
You said that at n equal 4 super Young-Mills, you don't have any confinement deconfinement transition, and probably you said that because of the scale invariance, because it's a conformal field theory, right? So the dual of that, I'm thinking, is type 2 supergravity in ADS5, cos S5. space-time. But what if I put a black hole in there, so a black rain? Then you have to if I want to consider n equal 4 superemits at non-zero temperature,
Right.
you should have a transition between thermal AdS and
No, this is actually not a thermal gas, you mean. So this would be very similar to what's Hawking-Page transition, which is known from previously from before.
Yeah, I know it shouldn't be true, so I'm just confused right now.
This is actually true if you consider, for instance, n is for subyoung males on a spherical boundary. So then you would have AdS, which is global AdS, and then this actually can happen. So it's very easy to see why it cannot happen in what I call normal AdS CFT. People in the GR community will complain about this because they consider. Okay, I should draw this a little bit because there's difference between global AdS and punk AdS. It's kind of important, but I didn't want to cover that.
I actually covered this yesterday.
Oh, you did? Okay, fair enough. Nice. Okay, good. Well, no, it's not so bad to repeat it in a different point of view, I suppose. So global AdS is this thing where you have your sphere over here, which is the boundary, and this sphere, of course, really has the radius of the sphere. So it's like the radius, like, I don't know, did you call it R or something like that? And Poincare AdS is really a patch of this. So GR people always complain if I say, well, I really want to focus on Poincare AdS, they just say, yeah, you're considering this triangle, but you're not considering the full space, because there are actually nuclear acids in Poincare AdS, which cross this called Poincare horizon, and they go perfectly forward further in global AdS. So this global AdS is more or less like the complete picture of gravity with a negative cosmological constant. But in AdS CFT, you can consider both global AdS or Poincare AdS, and global AdS is really considering where the boundary CFT is living on the sphere. So the sphere would go in a circle here. Whereas this is kind of a conformal compactification of the sphere. So conformal compactification of Minkowski space. So this is a completely infinite flat space without any scale. Whereas the global AdS picture actually has this intrinsic scale, which is just the scale of this sphere. And then you can ask the question, like, what happens if I put like a black hole in the middle? For instance, you put a black hole over here. The black hole also has a certain size. The AdS radius is a certain size. So you can consider like the length scale of the black hole compared to the length scale of the AdS boundary. And this number can be large or small. And that can give you like a deconfinement-confinement phase transition. And this is what in fact will happen. And you actually know that this will happen because you know that black holes in flat space-time, just in our own universe, they evaporate away. This is because they have negative specific heat, so if they send out some Hawking radiation and the mass gets smaller, temperature gets higher, and it basically explodes. Right? That is a well-known, the Hawking radiation basically. In AdS, funnily enough, this doesn't necessarily happen, because if you have a large black hole, these are called large and small black holes then, to really distinguish this effect, like just the black hole evaporating, exploding, or a large black hole, then there will be Hawking radiation going out of the black hole, of course, but it will be the boundary and it will be reflected back. And if this black hole is large enough, this reflection of the boundary compensates the black hole radiation, and there's equilibrium. And you really have a thermal black hole, and this is then a stable black hole, this is a large black hole. And so the thing is that this length, the radius of the black hole has to be larger than the AdS radius, then it's stable, and if it's smaller then you get this thermal gas, so this is the deconfinement-confinement transition. And then you also see that if you consider this Poincare AdS, Minkowski boundary, this you can just think about if you take a sphere with a certain size and you want to make flat space, but just take the sphere to be infinitely big, right? Take the limit. And then you see that the black holes are always large. Well, at least there is no scale anymore. So the black hole, you have to take the black hole always large. If you take the black hole to be small, it's just not. It goes to zero.
It's the radius of the compact space that is that radius of the black hole, and that's setting the scale. And then if you send that to infinity, then
there is no scale left anymore. Then if you can do this, and of course we do this actually, we have Poincare AdS, we have a black hole, but we just have one scale, we just have the temperature. And then you can ask me, is this a big temperature or a small temperature? Well, it's the only scale, you have to compare it with something. It's a scale, it's really the crucial thing of scale invariant theory, there are no scales. If you put in a scale, like a temperature, you can do that. You can put in also a string with a certain energy or something like that. So then you have the temperature and the energy of the string. You have two scales, you can compare them again. And then it's a sensible question, is one thing bigger than the other or not? But if you have a dimensional quantity and it's the only thing you have, then there are no sensible questions you can ask.
But how does that translate to the field theory side? You said...
Yeah, it's exactly the same thing. I mean, this is just dimensional analysis. In the field theory, you have skill invariant field theory, so it doesn't have any intrinsic skills like QCD would have. For instance, QCD has intrinsic skills, has the mass of the proton, has the confinement, deconfinement temperature, a lot of intrinsic skills. But if there are if these are all irrelevant, so if you are really in a regime which is approximately skill invariant, where there are no real dimensional quantities you want to compare with, then okay, you have to always compare two things, otherwise there's nothing you can have.
I guess what I'm asking, you made a statement n equal 4 superunits is not doesn't have a deconfinement confinement transition. Then I'm asking, what is the field theory that has a confinement deconfinement transition?
So if you put it on a sphere, for instance.
So it's n equal 4 superunits on a sphere, right? On a
that would have deconfinement confinement transition. Yeah. But you can also put I wouldn't be super excited about that because, okay, real world QCD doesn't live on a sphere. I mean, this is for all practical purposes irrelevant to real world QCD. What you can also do is put in some scalar, so okay, in this kind of diagram, there's like this is the boundary, this is then the AdS radius going inside. You can put some scalar field in it. You can put some potential of the scalar field, so then you would have the metric plus some scalar field, which also exists in 2B supergravity. And then you can either by hand construct a potential for the scalar field, or you can look something up somewhere, excite these kind of things. And then in these kind of potentials, you can put in all kinds of skills again, and then you can play the same game, and the same kind of things will happen. Okay, can happen. Yeah, people study this. It's interesting. Yes, Josh.
Can you say again how you said you put a large black hole instead of a small black hole? But you only have the temperature to control, right?
Yeah, or which is equivalent to the size of the black hole or the energy in the black hole.
So I understand you only have one parameter really, right?
Right.
You collapse a certain amount of energy, say. That gives you the size of the black hole.
More or less, yeah.
And so how do you decide? So I understood at some point that the transition, in Poincaré, you have this transition between the small and the large black hole at some
No,
point.
in global AdS. The global AdS, you have the transition between the small.
The Hawking page transition.
Yes.
But at some point in the Poincaré page, you also have this transition between the small and the large black hole, don't you? No. Okay. So that's also Poincaré.
Poincaré AdS, yeah, doesn't have any scales.
Okay, thanks.
There's no dimensionless parameter.
Yeah, that's also what's confusing me, that there's nothing to tune. Okay, thanks. That's my confusion.
Okay, yeah, sorry about being very slow. No, I think it's useful if you ask questions. I'm going a bit slower than I expected, as you probably expected.
You got 90 minutes.
I only have 17 slides, so it's not so bad. Good. So I guess I should go to Einstein equations, because that is something you will then use in your daily life if you want to study this black hole formation. And then the thing is that what we were going to use is this called characteristic formulation of the Einstein equation. On the next slides I have a bit more about it. But the crucial point of this characteristic formulation is that we'll use generalized Eddington-Finkelstein coordinates. I guess this slide is basically to say that there are two reasonable coordinates you can use to describe physics in this kind of Poincaré AdS spacetime. And this one is these null coordinates, so Eddington-Finkelstein coordinates are null coordinates. And you would write down a metric more or less like this, as opposed to Pfeffer-Graham coordinates, which are not null coordinates. So you just have like normal, for instance, Minkowski over here, and then a dc squared over z squared, which will be your radial direction, where z would be the boundary, would be at z equals 0. Here, there's an r coordinate, which is also parameterizing the AdS coordinate, but you see there's no dr squared. So that means if you just have if you have an equal time slice, so dt equals 0, you can move in r, and dt dr is still 0. So this is why this is a null coordinate. So basically, indeed, the picture would be in this kind of diagram. Maybe I should move a little bit of the inside, but it would be really this diagram, and you would have and t equal to 0 would be a slice like this, where this is then the r direction. And yeah, moving in r at constant t and constant other coordinates is really in no direction. Whereas these Pfefferman-Graham coordinates, they go more or less like this. They're space-like coordinates, much more like you're used to, in fact. So there has been some discussion, in fact, about calling this t or u, because it could be a null coordinate. Actually, it is a null coordinate, so it's people in the dr community, you would probably call it u. But I always call it t because this v. I see ingoing null coordinates as v.
Ingoing here.
Fair enough. Good. V. Well, I don't like this, and the reason I don't like it is because I want to focus on the boundary field theory. That's what I'm most interested in. And it is a null coordinate like in this AdS direction, but in the boundary it's perfectly your normal time coordinate basically. It's just normal time. Just the time in AdS runs the same way as the time near the boundary, just by looking at what happens near the boundary. So, and then, okay, in the boundary we don't even have this dr term, you just have like your boundary space-time, so it's a perfectly fine time coordinate, at least for the boundary point of view. And what I'll show you in the next slide is that if you assume a form like this, okay, I should say a little bit more why I choose this particular form, or basically I wasn't the first, but just Larry Joffe were the first to write down this metric as far as I'm aware. You put the dt squared, the xl squared, the xt squared, so you have like a longitudinal direction and two transverse directions and time. And what basically the idea of this metric is, we're going to assume for simplicity that nothing depends on the space coordinates. So no xl, xt dependence. And this basically means that the most general metric, you can remove the dt, dxl, or the dt, dxt, or dxl, dxt. So by this assumption that nothing depends on space, it's completely homogeneous. You can just, these three components are really all that is there in the most general metric. And this one, this 2, you can fix by some coordinate transformation. So this is kind of gauge fixing. So by coordinate, you can always make this equal to 2. So this is allowed to put like this. But we still, of course, want to have some non-trivial dynamics. Otherwise, it will be super boring. So what we do is we have this e to the power minus 2b here, e to the power b over there, which basically says that we can that the longitudinal coordinate and transverse coordinate can behave differently. And in our picture, this would mean, well, it's a very simplified picture, of course, considering the complicated dynamics over here. But if you look at the center of this plasma, perhaps it's approximately homogeneous, right? Perhaps it doesn't depend much if you're a little bit away over here in the transverse direction or longitudinal direction. I mean, it's not completely true, but perhaps it's a reasonable assumption to learn some of the physics happening in the middle over here. And then what we allow for is that basically the space stretches differently in the direction of collision, as opposed to the transverse direction, the direction perpendicular to the collision. So there could be a difference by allowing this different stretching, could be different pressure in this direction than in this direction, for instance. Depending on initial conditions, and then we want to kind of study. We expect, of course, that if the system thermalizes, behaves like a fluid, that the pressures in all directions become equal. And this is actually what we'll see happening in the problem session, that this B will tend to go to 0, but probably in these kind of setups, like these collisions, it will start out non-zero and then go to 0 to go to this fluid regime. So that's why we write down the metric like this. And these null coordinates is, well, that's the thing that dramatically simplifies these things. Null coordinates also mean, in this case, that, of course, if you start with some event near the boundary, like sourcing it here, or putting some bump here, or whatever it means, in these type of coordinates, they fall into the black hole instantaneously, because it's a null coordinate. But if you put something over here in the IR, actually, in the lower energies, it will take some while to hit the boundary, where the boundary physics lives, at least that's what people say. Because, okay, I have a slide about it, how to go from AdS physics to boundary physics. And actually, so that's also why I put down these Pfefferman-Graham coordinates, because if you want to extract actually boundary physics, usually these coordinates are the best way to write it. So there's kind of this choice of coordinates. If you want to figure out, this is called the holographic thermalization, so to get the stress energy tensor of the boundary, I don't know if you covered that, more or less, well, then you usually want to go to these coordinates, because everybody in literature uses these coordinates to get the stress energy tensor. So basically what we usually do is we go back and forth, at least near the boundary between these two coordinates. But for now I'll focus on this node coordinates. And I'll tell you a little bit more like what actually is behind this choice of coordinates, because it goes actually back all the way to the 60s by Bondi and Sachs. But I'll just show you the Einstein equations and try to convince you that this is actually very simple. Yeah, so this was first written down by Bondi, gravitational waves in relativity 1960s, really by thinking about gravitational waves in flat space, so very different physics, 4 dimensions. And then by Tesla and Jaffe 8 years ago now, this was, they realized, well, at least they wrote down how these things work in AdS, which is what we will use. And what you see is, this, okay, it looks a little bit complicated, but it's not so much, because this is, these equations have a very, well, I have a nested structure, which means that you can solve them one for one, and all of these equations are just linear equations in R. So basically, how you see this? Well, so we have to put some initial condition. In this case, you can see from the equations that if we just know B as a function of R, we can solve for the complete future. And how is this? Because if you look at the first equation, okay, if you know B is a function of R, B prime is dBdr. Did I put it? No, I didn't put it. This is the dBdr. So we can compute B prime because we know B is a function of R. And then this equation is a linear differential equation for S as a function of R. So you see that if you know this, it's just a linear differential equation, you integrate it, and you know S as well. And then the next step, if we know B and S then on this initial time slice, what we can do is we look at this equation. Well, this, so the S squared is now, of course, we know because it's non-linear, but we know it already from the previous step. S prime we know, S v prime. S dot we don't know yet. S dot is actually, I wrote it down on the next slide too, it's actually not the time derivative. This is one of the peculiar things about this characteristic formulation. S dot is really the derivative along an outgoing null geodesic. So you have ingoing null geodesics, so these are basically the R derivative, very simple. But the outgoing null derivatives, you have to solve a small equation. So this is that equation, it will be there on the next slide, so it's very simple. But what you can, so it's related to the time derivative, but not exactly that. If you know B and S, or actually only if you know S, you can integrate this equation to find S dot, because it's S dot prime, so it depends on R, but it's a linear differential equation for S dot. If you then know, well, then it just goes on. So you know S dot, S, and B, and then this again, well, it's B dot here, B dot prime here. So this is the coefficient for the derivative, and this is the normal, this is the source term, we know S dot and B prime. So it's just a linear differential equation to solve for B dot. And then lastly, perhaps the simplest one, you just have A prime prime, and we know all of this. So you solve for this, we also know A. So now we basically know S dot, B dot, A, well, everything, just by knowing B and integrating a few of these differential equations. This is then a constraint equation, which we don't actually need, and we can actually just use it as a numerical check. Okay, I should have said earlier, so this H dot is actually the time derivative of any function like B dot, S dot, is just the time derivative plus half times A times the R derivative. So basically, if you know B dot, and you know A, and you know B prime, then you know the time derivative of B. So basically, by doing this, just these 4 simple differential equations, we get B dot, we get dB dt, and then of course, if you know dB dt, you can go to the next time step and repeat the whole procedure. So this is basically why these Einstein equations, which normally are actually a horrible couple of PDEs, are super simple in this case. And I'll probably say a little bit later on that for these Einstein equations you need some boundary conditions, because they're differential equations, we need boundary conditions. So this complicates things a little bit near the boundary, but it's also easy to understand. Is this scheme clear? Because it's actually very important. I mean, this is the whole idea behind solving Einstein equations.
Is the B you put yourself, is there a specific thing that you be worried about when you define your B, or is it just?
So this is also a very good question. Yeah, actually, to some extent we don't really know what kind of initial B we would take in general. So for instance, when we study this, you can either generate it in some specific way, which is not so easy, or actually what we actually in practice usually do is we just take 1,000 different B's and see what happens in general. Because this scheme is so simple, you can easily do it 1,000 times. Yeah, I think it's actually, we don't exactly know, for instance, what, to rephrase the question, is we don't exactly know what this B means in the CFT. This is just the initial metric on this initial time slice, and what this actually means is we don't really know, unless, for instance, what I'll show you a little bit later on, which doesn't apply in this particular metric, but if you do like a collision like this, you have some initial state and you do the full kind of collision, then this B has a bit more meaning, because then you know the initial condition and you know something after the collision, then you can see how it relaxes. But yeah, you cannot, for instance, do a collision in a homogeneous setup. I told you I wanted just to do this homogeneous thing, and then you cannot do collisions. So either you have to work harder and then you know a bit more what this B means, or you just try a lot of things and extract some general lesson about it. Yes?
Sorry, I'm confused about something. So if I give you some B, can't you then just look at how it behaves near the boundary and understand whether I've turned on some source, whether there's a source deformation in my stress energy tensor, or whether it's a bad for the state? I mean, can't I?
So that is of course true. So if you give me some B, you can determine what is the stress tensor at that time. And if I know, actually it's true a little bit more generically, if you do this near boundary analysis, so if you know this B close to the boundary, so you know some derivatives, you also know some time derivatives of the stress tensor. I think it's more or less what you're asking, right? If you know, for instance, the stress tensor, you know some time derivatives, don't I know what B is?
Right, so my question is basically like, if my goal is to mock up something that happens at Rick, and maybe I can sort of imagine what should happen in the stress tensor as an initial condition, and use that to guide my intuition for what B I would choose. So I'm wondering if you could sort of reverse engineer a sensible B this way.
Yeah, we thought about that, of course. It's not so easy, because, so as I said, so the very close to the boundary, the behavior of B is related to the pressures of Rig, say. Right. And at Rig, people, at least if you believe in perturbative QCD, you would think, for instance, it's actually true, that the longitudinal pressure is minus the transverse pressure. It's kind of curious, but this is what people know from so-called color glass condensate. And that then you can do. You can have the you can put this B to have that particular form. I don't even know if the time derivative is actually known, but if you also know the time derivative, you would also know how the derivative of B is near the boundary. But then of course you just have two parameters, and this B is actually a function of R. So we have a complete functional freedom, and indeed in this case you can constrain it a little bit. This is a good point.
So I thought Chris's question had more to do with what you haven't talked about yet, right, which is boundary conditions. Like in that sense, you could probably fix the boundary condition if you'll do later, and then you have a whole bunch of bulk behaviors, that's what you're saying, that would equally fit, would equally describe exactly the same boundary fit. So I guess that's why Chris was confused, probably. You haven't talked about boundary conditions yet, which you will at some point.
For instance, in what Paul and Larry originally did, you start off with the thermal state.
Good,
you turn on a boundary metric, you know, that forces the fluid anisotropically and then it evolves according to the nice set of equations that you
I didn't want to go into that, but
it's completely deterministic and it's completely obvious what the B is doing, right?
So that's true. So if you, what in this paper is done, and maybe I shouldn't even mention it, they actually do it differently. They start with vacuum over here, and in vacuum you know exactly what B is. It's actually 0. And what they then do is they, instead of looking at field theory in flat spacetime, Minkowski, they're going to look at a curved theory. So they basically really look at the CFT in curved spacetime. So they basically deform the boundary metric. And then these Einstein equations are completely well defined. And then at a certain B, you can just you can just compute what B is, given that the curvature of spacetime was what it was before, which they post in their paper. I didn't say like this because, of course, this is not what happens at a heavy ion collision. It's not that suddenly space-time gets curved in the accelerator, like the CFT space-time. The AdS space-time gets curved, but of course these heavy ion collisions don't have anything to do with gravity from a QCD point of view. So I was thinking more like Chris' question, like in a heavy ion collision, what kind of B should you choose? And that people don't know. If they tell you an academic problem like we curve boundary space-time in such a way, what is B? Okay, you can actually say it. But I would then say, okay, then do the whole thing, right? Then do a collision like actually what Paul and Larry did later on, where just everything is flat, you do a collision, and you can compute what B is. But in this type of problem, well, You see, it's a good question. Yes?
Can you choose a B that breaks stuff? Can I choose a wrong B?
Yes, you can definitely do that. That's actually also a funny thing to study, because well, I don't know, it's probably a little bit academic too, but what happens, so I didn't go into the boundary conditions yet, but it turns out you have to choose B, but that doesn't fix the energy density of your field theory. So we also have to one other number to choose, which is basically either the final temperature or the energy density. And the thing you're not allowed to do, at least if you believe in cosmic censorship, you can form, for instance, you cannot start with zero energy density and have some difference in pressures, because then what turns out in Einstein equation, you get a naked singularity from the start. So, okay, you can write down naked singularities in GR, of course, but we usually think it doesn't make sense. From a field theory point of view, you also think it doesn't make sense, right? If you have you cannot have different pressures, negative and positive, if you don't have energy. So there are constraints on this profile of B if you give me some energy density. And a funny thing is, for instance, that it turns out you can choose this B profile in such a way, for instance, that the transverse pressure is 1,000 times minus the negative pressure. So a huge pressure difference, a huge negative pressure. It sounds a little bit physical, but in this AdS type of profiles we can do this, but only for a very, very short time. So then it has to, that basically means that this B is very excited near the boundary, so we have a lot of difference between the long to the transverse directed next to the boundary. But if we choose it over the complete profile, we have a naked singularity. But if you do it for a very small amount of space over here, then it just lives over a very small time. And then, well, I used to say that this field theory can actually support this pressure anisotropy for like a time of, well, 1/1000th of the inverse temperature if you fix your units, the energy density to a temperature. So there are constraints, yeah. But this we just found out by trial and error. Does it make sense? Yes.
So if you make the negative singularity the part, what happens on the boundary at you are in the right time?
So I can only answer, I think, by example, but I mean, well, the trivial example I gave was zero energy density, positive pressure, negative pressure. That would correspond to naked singularity. Something I think we cannot do, if you believe in cosmic censorship, and I never managed, is to start with a perfectly sensible initial condition and then form a naked singularity. Then you would really be able to answer your question, right? Well, what happens in the field theory when you form a naked singularity? But that we never managed. I mean, never solve violations of cosmic censorship. So you can just write down a state which is not allowed, and okay, then yeah. But I
think from the boundary point of view, you don't know if the negative singularity was created until that negative singularity is the boundary. And until that, your field evolution seems healthy. And only when you know that the negative singularity is the boundary, your field theory computation will break down.
Okay, so you say, and this is actually true, of course. Imagine I start with some B, which looks a bit like this, for instance, and you have a naked singularity over here. We can perhaps still do the AdS computation in this domain, because by causality, the naked singularity cannot enter this domain. So the naked singularity can hit the boundary over there, but this regime we should still be able to compute, and we should still be able to do some field theory computation over there. And this is of course true. Yes, it's still, of course, then so this state is still not allowed, but it basically tells you that putting the negative singularity over here gives you some kind of long-range correlation, some correlations in your field theory which are long-range, so they don't affect like the near boundary base over here, which are not allowed. And in fact, of course, doing this type of evolution, you could also put a lot of energy here. You could also do that. Well, maybe not actually. Maybe it's not.
I'm sorry, I really don't understand what's going on anymore. Like this, let's take a related example in field theory terms, where we would say that if I started playing this game, it's garbage in and garbage out. Consider instantons in U1 gauge theory in 4 dimensions. Formally, they exist. They're singular field configurations that have F wedge F non-zero. But I mean, there's singular field configurations. There's some saddle point, it's singular, and they don't correspond. They don't don't tell you anything about the
yeah.
space of honest to God electromagnetism.
I was asked about it. I'm not saying that the naked singularities are something you have to look into. I mean, I just said don't do the naked singularities. Okay. Yeah. But it constrains you. Because it is a little bit relevant because we don't really know how to start with B. And if you have to choose some initial profile, and you can do this the wrong way. So that's why I think it's a little bit relevant. But then you can do these things, and okay, so let me then not do the near boundary expansion. So it was also part of an optional part of my problem set. So you can do later on solve Einstein equations near the boundary, order by order, get all these functions A, B, see exactly how they behave as an expansion near the boundary, and that if you know this near boundary expansion, you know of course how you need to put your boundary conditions of this in this scheme, and I'll just then tell you that you can also, if you do this near boundary expansion, this also relates back directly to which I'm then also not going to go into, to holographic renormalization, which in terms of the near boundary behavior of your metric, okay, it looks like a complicated formula, but this is just the first term near boundary expansion, the second term at the near boundary expansion of the metric, and the fourth term at the near boundary expansion. If you know these terms, this basically tells you what is the expectation value of your stress tensor of the CFT, which we want to know. And I think maybe it has been covered yesterday a little bit. It's to know all the details is not required for the rest of nor for the problem, nor for the rest of the lecture, so I think I'll skip that if you don't mind. But of course you need to know that you need to do this near boundary expansion for two reasons. The first reason is that you need to know what are these near boundary terms to obtain your stress energy tensor and the pressures and the energy density which you are finally interested in. And if you then do the near boundary expansion, you also know that this energy density is related to these boundary conditions. So what we'll need is that for this particular differential equation, it turns out that if you know B, you don't know enough. You really need to put the boundary condition for S dot, which is related to the near boundary expansion, because there you put the boundary condition, and it's related to the energy density. So that's basically all you need to know. So that's where this comes in. If you know this energy density and you know B, then you also can figure out what are the boundary conditions for the other two. They are related.
Maybe a comment to connect to yesterday. Christian wrote down the energy momentum tensor of the field theory, but in terms of the extrinsic curvature. And so that might look somewhat different from the way that you write it down.
Energy density as a function of extrinsic curvature. So it's basically in this formula, but
just this formula in a more covariant looking form, but it's the same formula, which is what Matthias is emphasizing.
Which is what?
Huh?
Which is what Matthias emphasized. Okay.
Yeah, what Matthias is emphasizing is this formula is secretly the same formula as what appeared yesterday.
Good, good. Yeah, these things can be written down in a way. But okay, so to come back to this, to close this thing of the. Okay, I think I did this. Well, let me say this. So let me say what was essential about these characteristic Einstein equations, which is basically the same thing as these null Einstein equations. Get this nested scheme very easy. So the three essential things were basically to use generalized additive Finkelstein coordinates. What we also did in this form of the metric, which is also essential, is that we have to separate out the spatial determinant of the metric. So if you look at this metric, you see I didn't write here A, B, C. Could have done that. But this is of course equivalent, that we have like an arbitrary function S and B, where this one is S squared e to the power minus 2b, and this is S squared e to the power b. And if you look at the spatial part of the metric, so these two, then of course the determinant of this is, there are two transfers to coordinates, so you have twice this one, e to the power b times e to the power b, times e to the power minus 2b, cancel, so the determinant of this part is S to the power 6. So the determinant of the spatial part is one single function, and it turns out if you do this the naive ABC case, then you ruin this structure. So that is something that comes back to this paper from the 1960s. And the last thing, which I already mentioned, is that you don't write your equation in terms of time derivatives. Also doesn't give like the nice nested scheme, but you have to write your equations in terms of outgoing null geodesics. So that basically, well, okay, you can already see it from the metric. An outgoing null geodesic has to cancel this one, so there's like a t derivative, but there's also a times the r derivative, and then if you work out like what is, if you go in this direction, if you work out what is, if it's null or not, you'll find this is a null direction, or you just take it as a definition. But this is a little bit tricky. Yeah. Okay.
I'm sorry, maybe this is kind of an annoying question. I was just curious, do you know why writing the equations in this way with this sort of outgoing null direction as your time derivative leads to this nice nested structure? Like, do you have some sort of intuition as to why this works? I sort of always wondered that.
Yeah, I thought quite a lot about it. I think my final conclusion was that I don't. Yeah, no. I don't know. It's also, it's definitely not in the papers. Let's put it like that. Yeah. So yeah, but this is how things simplify.
I asked Larry and he said gave the same answer more or less.
Right. So that must be true. But okay.
Does this remain? I mean, has anyone ever checked this? If this remains true, if you add, I don't know, generic scalar matter content to the bulk, or
yeah. Larry and Paul have this long paper where they work out all these things.
Yeah.
And it remains. I think it remains almost entirely true. There is one complication. Well, so it works for any dimensions, for any type of thing. So that's very nice. I mean, of course, the equation gets longer, but the same structure remains. The only complication is if you add Maxwell equations and you want them to back react. So you get some source terms of the back reaction. This is just gravity. But if you add some extra fields, of course, they also could back react. So they could curve the space by itself by Einstein equations. Then these things still become linear differential equations, but some of them couple. So then you would basically have to solve two linear equations at the same time. But this is still an easy problem. So if they become non-linear, it becomes a complicated problem. But because they're just coupled linear equations, basically the problem really becomes just twice as hard, which is relatively easy. I could tell you more. Actually, I could tell you more about it if I get to do the spectral methods. I'm not doing very well on time, right?
No, you're fine.
Let's see, but
we have time.
I have 11, but it's actually 10, right?
You have until 10:45, I believe.
Oh, okay. Oh, I'm not doing. So then it's good that you asked all the questions. Good. So this is the essential things about when these things work, and it works actually very generally. And well, I think some of you know that now actually Larry and Paul actually managed to solve the system very ambitiously and technically complicated in full generality. So they really started with a 5-dimensional. They really solved the 5-dimensional general relativity problem, which is a big achievement. I have one slide at the end where I'll show their results. This is of course simple. Okay, I think I told you already about there is this. So this is constraint. So well, in general relativity they are called constraints, which just means that if you have an initial metric, initial time slice, you cannot choose these functions a, s, and b arbitrarily. And this is well known in general relativity, but it's also sometimes a very big problem for them, because they just want to start with some initial condition, and then it turns out it's inconsistent with Einstein equations. Can happen. And these constraint equations, they can actually be very complicated on themselves. If you want to know how this works, you should ask Hans. It's very complicated, right?
I'll talk about it. I'll show the...
It can be very complicated, let me put it like that. In our case, it's completely obvious, because in our case, well, we could actually choose this b completely arbitrarily, but then our s was fixed. So we cannot change these two things arbitrarily, or a, s, and b arbitrarily. I mean, there are definitely constraints, things you can choose. But if we know b, we just had the simple equation to solve for s. So instead of having a complicated constraint equation, we have a very simple constraint equation. So we see this in this obvious way. There are two constraints. So one is actually this b to s thing. So it's much easier than in this called ADM formalism Hans is using, or generalized harmonics is related to ADM as far as I'm aware. The other constraint equation is actually this last equation. And this one is actually not a constraint equation on the initial t slice, but it's actually a constraint equation on an initial r slice. So this one is actually a constraint equation which we will which means that as a function of time it has to be satisfied somewhere, but then we don't need to worry about this equation anymore. And how we actually will use this equation in practice is just to implement it at the boundary. So we look at our near boundary equation, we say this equation has to be satisfied near the boundary, and then okay, it's a constraint equation, so it's satisfied everywhere. Should be at least, should be. And how do we do it near the boundary? It turns out this constraint Einstein equation is actually equivalent to conservation of the stress energy tensor if you use this formula. And in our case, this is a homogeneous setup, so it's very simple. And it just means that the energy density is constant as a function of time. And this is really encapsulated in this equation. And after that, we don't need to worry about it anymore. But you do actually have to worry about it because we're going to do these things numerically. And it's actually it's very nice because, or essentially, you can also probably say that what I always do, I would compute this equation. Well, I would compute everything, and I would compute this equation, and it has to be 0, of course, because it has to be satisfied. But then there are all kinds of numerical problems, or instabilities, or whatsoever. So if you do something, if you do anything wrong, then this equation will not be 0 everywhere. And if this equation is like 10 to the minus 6, then you claim victory, and you probably know that you have a good solution of Einstein equations.
But that doesn't stop you from considering setups where you pump energy into your system, right? Should that just show up as a source term in that last equation?
Exactly. Because what I said was indeed that we usually implement this near the boundary, and of course near the boundary. In this case, actually, like how in this case Skanderis and others wrote it down. This is the most general form. If the boundary, so the statement that the energy density is constant, it actually assumes that the boundary metric is completely flat. If you curve the boundary, basically by this formula more or less already you can almost already see it, then you pump in energy to the system. So, but this is fully determined by the near boundary expansion by having boundary conditions which are curved. So you have to do this order by order solution, you have to, and then you get some equation. You have to solve Einstein equations order by order near the boundary, given some boundary conditions for how the metric falls off at the boundary. Well, it's easiest to see. Well, it's easiest to see in this formalism, but here you can also see it easily. What you say is this d mu nu as a function of all coordinates near the boundary. It's an expansion in z, and the first term, well, in our case, will just be Minkowski, so very simple, minus 1, 1, 1. But if you do a more general boundary condition, then if you do the order by order solution, it will become more complicated, and you will also find that the energy is not constant. It will be some specific equation which you have to solve. Good.
What was the comment that you had about scheme dependence and this paper creates this?
Yeah, that's a funny thing.
And it's totally aside from everything else. We've already harassed you so much, and you should just keep going.
No, well, I guess I was just worried about it recently myself too. So I don't actually fully understand this, but Skanderis et al. They claim they understand this. This is actually, so this formula gives you the stress energy tensor. It looks like a very nice closed form formula, but what actually happened is that there is a term here which is arbitrary and neglected. And this term is, well, it's called H4. And why is it called H4? It's because you do this near boundary expansion and you get this G0. Okay, this is your boundary condition. Good. G2, okay, you compute it using near boundary expansion. That also works. G4 is not really determined near the boundary from the boundary conditions, but you solve it by using this complete evolution, and we just extract it as a result. But then there's also a logarithmic term if the boundary metric is curved. And it turns out that this stress energy tensor, if you do the renormalization, basically either in AdS or in the CFT, if you renormalize, you need to choose a specific scheme, or you have to cancel counter terms, and well, this is what these people do, and this is how we're taught to do renormalization. Then then there is this if this boundary metric is not flat, there is a counter term which has some finite contributions, which yeah, you really have to.
Okay,
to
we're
fix.
talking about the R squared counter term.
So is this the same term that appears only for even space, even boundaries?
It's only for even space dimensions.
Maybe I can say some a couple more words because it's actually
perfect.
And-
Sorry about it. Sorry about it.
No, it's okay. This is a well-known thing that goes back to spacetimes. So Wilke said everything right. But the point is, from a field theory point of view, you can think of the fact that if you've broken conformal invariance somehow, then the ward identity is going to tell you that the trace of the stress energy tensor vanishes up to how you break that conformal symmetry. So for example, you have some freedom. Let's say I break it with some scalar operator, with some trivial scaling dimension. So maybe if I turn on the source for that operator, that will appear on the right side of that ward identity. There also could be a term that's like, when you integrate it, it should be conformally invariant. So for example, the Lagrangian of a scalar in 4 dimensions. So this can also appear. And so by adding finite count, sorry, I'm only talking to you, but I want to talk to everyone. So by adding finite counter terms to the on-shelf action, to the near boundary action, you can artificially adjust this coefficient. And so absent any sort of supersymmetry or some guiding principle by which you should fix the coefficients of these finite counter terms, they're a priori undetermined. And so
But
you have to pick some
at a
scheme,
technical
which
level,
is
your
what-
statement is that you could always, given you say compute the stress tensor in one scheme, say you compute it in another, the two could differ by the first variation of the counter term. In this case, since the only source he's turning on the metric, the only counter term that would be available is just scalar curvature squared.
yeah, exactly, things like that.
And, okay, so there could
And
be
so
some extra
Right, so
super
there's a conformal
local-
anomaly, like he says. There's a matter anomaly if you add some other stuff, and so it's dimension dependent for both the matter fields and the space-time dimension.
Okay.
I partly pointed it out, well, because of this paper, their paper perhaps, but also because it's a little bit funny, because if you look, for instance, so this is famous paper by Jess and Jaffa where they actually source the boundary. So they have non-trivial D0, and they have this conformal anomaly, and they have then this scheme dependence. And in their paper it's not completely apparent. And they actually plot like pressures, like going like this and this and this. And you look at, well, that's just because they fixed their scheme in a particular way. They could cancel all of that. I mean, so they have some pressures which fluctuate, but nothing actually physically fluctuates. It's just scheme dependence.
That's not true, though.
Yeah. If in the regime where this boundary metric is curved,
say that you pick the scheme where the D term in the anomaly is tuned to 0. That's a natural. That's the scheme they work in, right?
Minimal holographic subtraction.
Yeah.
That's minimal subtraction, but if you choose I mean, if you compute this term, it actually fluctuates exactly the same way as the thing that.
So your statement is that you can pick a choice, a different scheme.
Right, where everything
for which
looks.
the stress tensor looks much.
And usually, well, okay, I'm not sure if I really understand why some scheme is preferred over another scheme. Well, maybe Chris knows.
This is like a well-known problem in holographic applications, because unless you really have some guiding principle for fixing those finite counterterms, you really don't know them. So for example, let's say that I know that my field theory should be supersymmetric.
Right.
This is a good one, right? Then I know that maybe evaluated in some supersymmetric state. So basically, finite counterterms you add to the action, but you evaluate them in any solution. So for example, imagine that I take some BPS domain wall solution that I know should preserve some supersymmetries. I compute the stress energy tensor and evaluate it on that solution. And I know that, for example, the energy density should be 0 because it's supersymmetric. This will then fix this undetermined coefficient once and for all in my boundary action.
It should be a state-independent statement, though.
Well, no, I'm saying you need to know something about the state to make that, right? Because stress energy density won't always vanish
to
in
write
every
down
state.
the superconformal anomaly, which will hold in any state.
Sure, okay, but let's say I want to fix these terms that appear in team union, right? So this coefficient will be there always, but unless I know that team union is 0 in some specific configuration for some state, then I don't have any other way to fix that coefficient. So
Let's move
sorry,
to
maybe
the
we can talk about
discussion,
this
but
later,
I think it's an interesting discussion. But okay, in any case, I want to say that in for the heavy ion conditions or something like that, the metric is always boundary metric is always flat, and we don't actually have this issue. If you don't know, we don't have this performance.
That's true. That's it.
Then how much time do I have left?
Time is it? I think 20 minutes.
Good. So I guess I wanted to. Okay, I'll explain briefly what I wanted you to do during the problem session. because that relates back to why I explained these things. And what I actually wanted you to do is to not solve this complete nested scheme, what I just told you, that would require a little bit more time, but to solve these Einstein equations in a linearized way, which means basically you assume you start with a metric which is a thermal, just a black hole metric, just with some temperature. Okay, this is an analytic solution of Einstein equations. And then we want to solve Einstein equations as a linear perturbation around the black hole. So basically you take this metric, but you take like this piece plus a small perturbation, and then you expand these Einstein equations around this one. So epsilon, you take the linear term, and then what you will find, you don't even have the nested scheme, but what you have is just a single equation for B actually. So that is what is the second step, to do the Einstein equation reduced for B. And what I didn't really want you to do was to do this full near boundary analysis, but you can actually do it. It's a very good exercise. It's optional, but I just wrote down that actually if you do it, the near boundary expansion would go like this B would go like c to the fourth near the boundary, where c0 is the first term and it's the boundary. And then there's some coefficient which depends on time, and this coefficient is actually the thing we're interested in because this determines the pressure anisotropy. And then we get an equation for that. Okay, but it goes like c to the fourth near the boundary, so it's a little bit nasty to really solve numerically for this function delta B usually. Because, well, if you then want to, for instance, extract this B4, how do you do this? Well, you would perhaps take 4 derivatives, or you look very closely to the thing and divide by c to the fourth and see how it goes to 0. That's numerically not very stable. What you usually want to do, and what I want you to do, is to redefine this delta B. Really trivially, that you have a regularized delta B, which is this delta B over c to the fourth. Because then this delta B regular is just at c equals 0, it's just B4, and it's perfectly well behaved, nice and function. You rewrite the equation in this form, and now it should be a nice equation to solve numerically. Well, the thing is that this is a little bit, in some sense, a little bit too simple, because if you put this equation, it's an equation for c and t. If you put it into ND solve, Mathematica will spit out the answer. Okay, it's simple. But I wanted you to do the spectral method because I think it's useful. That's how we do this nested scheme always, because then Mathematica will not give you the answer. And the spectral methods are, well, very general way of solving differential equations, so it's useful for you to learn it anyway for any problem you might be working on in the future. At least, well, given if these are appropriate, but they're a very nice method to know. And what I want you to do is this, so this delta B will be an equation. The second, well, it's an equation C and T, partial differential equation, but it's linear. And what you then can do is, if you have some delta B at some initial time, t0, we'll take it to be 0, say it's 2 times c to the fourth, but as we discussed before, you can take something similar, something arbitrary. If you choose it too crazy, it will go wrong, but you'll quickly find out it will go wrong. So you can choose basically anything, that's your initial condition. And then we will rewrite this differential equation in terms of well, we will actually solve, it will be a differential equation Z to solve for the time derivative of delta B regular. Because that's of course what we want to do. We want to have this delta B, we have some energy density. Well, I said here take the temperature 1 over pi, so it's an obvious choice because then this thing cancels. You can choose something else, that just fixes your units. You give some delta B, and then you want to compute the time derivative of delta B as numerically with the spectral methods. I'll just explain you in a minute. And then, okay, then I said, okay, you can do the time stepping yourself, doing Runge-Kutta, Adams-Bashford. You can do it completely numerically, that's what we usually do. But you can also just use ND solve actually. You can just say, well, I have this delta B as an initial condition. I have the time derivative of delta B is, you make a function in Mathematica, and then you say time derivative is this, and then you solve as a function of time. And then Mathematica does the time stepping for you. Actually, this worked out very well for me because normally then Mathematica has all kinds of checks what kind of time steps it will take, and it has some adaptive time stepping, which is it's actually quite powerful. So this is not necessarily bad, but you can also implement completely yourself. But that's just using ND solve, so it's easy. And then then you're actually done. So this is actually why I thought it was a nice exercise, because then if you notice before the pressure anisotropy, so the longitudinal minus the transverse pressure is just 3 times before. You can plot it as a function of time, and you'll see that it goes to 0. It will thermalize, and it will go to the hydrodynamic description where these things should be equal. And what you can see immediately if you plot this, you will see it, I hope, is that this thing, okay, so it will oscillate towards 0 and it will also damp. And this is characteristic of quasi-normal modes of black holes. And just by plotting this thing, you can just extract the frequencies almost on the spot. So that's the exercise I wanted you to do. And that's also why I wanted you to explain these spectral methods.
Okay. I have a question.
Yes.
So is that linearized equation for B is basically the one that becomes probe scalar in AdS geometric background?
So this is something which turns out to be true. That if you solve the linearized, even like the linearized equation for B is equivalent to scalar to solve a scalar equation in AdS. That's true. Good. So okay. So spectral methods. They basically, I wrote down 2 simple examples here, which I'll solve a slightly different one in Mathematica for you in just a moment, where you have an equation which is, well, it can be linear and this one can be nonlinear. If you're nonlinear, you use Newton's method. We won't do that today, but it's almost as easy. What you do in spectral methods, or I should actually say pseudo-spectral methods, you basically have your function and your differential equation. So you have a function y of x, and well, okay, we want to solve for it, of course, but it will look something like this, say, something like that. And how do we solve for this numerically? Well, obviously we need to represent this, the values of these functions on grid points. And the trick, actually, almost the entire trick of spectral methods is to use more grid points near the end points, and in the middle some fewer ones. And then use a very accurate interpolation scheme. Why, I don't want to go into all the details, like how there's a lot of theory behind this spectral methods. But what it basically does is it takes the values of the function on these grid points, and then it constructs, if you have like 20 grid points, you can view it at least in this way. You can either say it constructs a Chebyshev, all kinds of Chebyshev polynomials. They look something like this or something like that. It takes these 20 grid points and it takes then the first 20 Chebyshev polynomials, and there's a one-to-one mapping between these grid points and the sum of these Chebyshev polynomials. So then you have like, then of course, given these 20 points, we have a functional representation which at least is accurate on these grid points. And between the grid points, of course, you don't really know, but the hope is that we will converge. This is one way to see it. I prefer it to some extent, which is also true. It's another way to see it. Is that what spectral methods do is if you have these 20 grid points, it will just construct a 20th order polynomial on x, so like a constant plus x with a coefficient all the way to x to the power 19, it would be then with the relevant coefficients. So this is why spectral methods are sometimes also called an all-order interpolation scheme. It will construct this 20th order polynomial, and that will be the function which these 20 values represent. That's a fairly easy way to see it. I mean, this is how at least it works in practice. We don't actually do this, but this is the idea behind it. And then you also see a little bit if you, I mean, let me oppose this to finite differencing schemes, which usually take, like, if you want to take the derivative of a function at this point, say, what do you usually do? Well, you take maybe this point and this point, and you compute the derivative. If you're a little bit better, you take like 1, 2, 3, 4 points. You construct like a third order polynomial, and you take the derivative of that polynomial. That will be a finite differencing scheme of finite order. So that is kind of the opposition between this all order scheme. This one is obviously more accurate to some extent, because if you have a finite differencing scheme and you have some grid point distance which is delta x, then okay, the error usually goes, if you have a fourth order delta finite differencing scheme, the error usually goes like delta x to the power 4, right? So if delta x is small, the error is small, but it's still finite, and in this case, in principle, if we're doing everything correctly, the error will go like delta x to the power 20, which is actually very small. But so that's the idea, and the essential point is what you really have to do is to put more grid points to near the end, and this is because this was an all-order scheme, and if you don't actually do this, what usually will happen is it will fit this high-order polynomial, but if you just do it like this, where you have like just grid points equispaced, you can try it for fun, well, it will find an exact solution 1-to-1, but the solution will usually look a little bit like this, which is exactly right at the grid points, but completely rubbish everywhere else. So that's just why you take more grid points at the end point. Okay, so that's the introduction to, well, so that is how we present. Oh, this is not the idea. Oh, I was holding this thing, of course. Okay, so the grid points, in practice, what you choose is this grid point xi is cosine pi I over n, where I in this case goes from 0 to n. And of course cosine goes from 1 to -1, and it goes a bit more slowly at the edge than in the middle. So this is exactly doing what we want it to do. Those are the grid points. And then the nice thing is that we can use this spectral, this interpolation scheme to, if we don't know the function values, we were interested, for instance, to computing the derivative numerically. And then what is the nice thing to realize is, well, taking a derivative of a function is a linear operator. Now we just have these 20 values, so this is kind of the function y is just a vector with 20 values. We taking derivatives of a linear operator, so what is it taking a derivative? It's just multiplying it with a matrix. But it's of course a specific matrix we want to then compute. Well, okay, we don't want to compute this, that's a little bit complicated, so you look it up in a book. So this is how the matrix looks like. This is what Boyd does. Or if you're lazy, you can also find NDs or finite difference derivative. So this is actually this finite difference derivative I was talking about, which can be second order, third order, fourth order. But you can also put the order to be the highest order possible, and then it's actually equivalent to the spectral methods. So what you then have is you have your function as a vector, you have your matrix as a derivative matrix. And then the nice thing is, of course, that this equation, which is a differential equation, is linear, becomes a very simple matrix equation. Because what we basically have is, okay, we have this equation, this is 0, we have our function y here, which is a vector. This one, of course, we want to compute, we don't know what y is. But now we more or less know what it is, because y prime prime, this is a term which we, I usually call d to spec, is a matrix, acting on y, gives you the second derivative of y. Okay, I put another one, plus y prime, so this is plus the other spectral differentiation matrix. And then there's a constant, a diagonal term, which just multiplies every term with -20 times x. And that is then rewriting this differential equation as a matrix equation. And because these spectral methods are so accurate, usually 20, 25 grid points is really enough. So this whole differential equation just amounts to solving this linear matrix problem, or basically inverting a 25 to 25 matrix, which any computer can do under a microsecond. So let's see. I wanted to show this how to do this in Mathematica, but well, maybe I can still do that. But then I have to do it quickly. Does it not do it? How much time do I have?
10 minutes.
Okay, let's do this, and in 5 minutes, and 5 minutes for the research, and then that's good. So, okay, so here I put slightly different equations. So I have this, basically this linear differential equation we want to solve. So it's slightly different than I wrote in the PowerPoint presentation. It's like y prime prime with some coefficients, which are could be in principle completely arbitrary. I chose a somewhat simple equation here because it's nice that Mathematica can solve this equation, so the linear differential equation. I also put two boundary conditions, y minus 1 is 5, y1 is minus 1. You can put anything you want. You can see that Mathematica with dsolve actually can solve this thing. It's complicated, but you can solve analytically, which for us is nice later on, right? Because then I can show you how accurate the numerics is, so it's a good test. But the spectrum apps will solve anything. And the solution, I think I wrote it over here, it looks like this. So indeed, so at 1, it's 1, and at -1, it's 5, and it looks a bit like this. So this is how Mathematica solved this with dsolve. How do we do this spectrum methods in practice? So I already said that we had to use this, well, I always make this a kind of init grid function. It takes a number of grid points. I call it nx, the number of points. And then x are the grid points. So what do? Init grid, we take like 25 grid points. And indeed x, you see, it returns x, and it goes from -1 to 1, and you see that, well, it's 0.99, 0.96, there are more grid points close to the edge, and then it goes a bit quicker. This is this cosine thing, which I put on the slide. But then the essential thing is, of course, that we want to have this differentiation matrices. And I said you can copy it from the book, but in this case I didn't want to do that. I just did the ND so finite difference derivative, which directly gives you this differentiation matrix. If you evaluate it with differentiation matrix, something you have to look up in the help, or you can get it from this notebook we'll put on the website. So this is the first derivative it will compute given these grid points, and the difference order is the maximum order you can get. It's always 0.9 - 1. So this gives you this differentiation matrix I was talking about. And if you want to take the second derivative, well, it's a linear operator, you just apply it twice, right? So it is a matrix, so you just applying the matrix twice, you just multiplying the matrix. This gives you the second derivative operator. Now to implement the scheme that I did, it's pretty easy. I want, of course, to make this matrix I was talking about there. The matrix we need to multiply y with to get this equation. So remember, the equation looks a bit, oh, now of course we have this x already evaluated. Maybe we don't want it because then, okay, so you could consider giving that a different letter, but sometimes this is more convenient, sometimes that thing. So what you want to do is, so basically with this matrix we'll have three components. The first one is the component with the second derivative, the second one is with the first derivative, and then there is the constant term in the matrix. Basically, this one is supposed to be multiplied by 2 plus x. This one is supposed to be multiplied by an identity. And the last term, the constant, without applying the differentiation, is just supposed to be multiplied by minus 20x. It's also a source term, but okay, if you put a source in this equation mathematically, I cannot solve it analytically anymore, so then it doesn't work. But in principle, it could be a source where if y equals 0. So what I do is just, for instance, in this case, I did it for arbitrary things. So if you take from this differential equation the derivative with respect to y prime prime, you just extract this 2 plus x. So basically, what this thing does, applies second derivative on the function we want to multiply. And then it multiplies with diagonal matrix with this 2 plus x, which we wanted it. I mean, the x will be, of course, the grid points, right? That's what we're talking about. So that's how we construct these differentiation matrices. So I put in the grid again, so now the x is evaluated again. And now the equation matrix is there. The source is actually just 0, because with 0 it could be a source of the equation. And then, well, I told you that we are going to solve it, but unfortunately it didn't work. Why didn't it work? That's not a question for you, of course. Somebody must be able to figure out why this was too naive, it was too fast. Sounds perfect, right? Well, if you look at the equation, do you think this solves the equation?
Sorry, zoom in a little bit. Can't read it.
Oh, zoom in a little bit. Yeah, good. Sorry about that. That might be too much. Still nobody sees what I did wrong? Yes.
I think you got to put the boundary condition.
Yeah. Okay. I mean, if this equation is y equals 0, okay, 0, 0, 0 is 0. The equation is satisfied trivially, but okay, we forgot about the boundary conditions, right? Because we also had LDE boundary conditions, and these are clearly not satisfied. I didn't even worry about them. And actually, Mathematica even complains about trying to do this, you see. And the reason why it even complains about it is if any matrix you make in this way, usually, at least, there are actually other examples, is not invertible. And the reason is very simple, because if you have a differentiation matrix and you act on it on a constant function, well, what's the derivative of a constant function? It's of course 0, and these differentiation matrices are not so bad that they really would give it 0. So basically, this differentiation matrix is a 0 eigenvalue, zero eigenvalue, so determinant 0, so you cannot even invert this matrix. And you also don't want to be able to invert this thing, because you need to put like a boundary condition somewhere. Alternatively, you could say, okay, 0 eigenvalue, so the rows in these equations are linearly dependent. If you take a second order differentiation matrix like this one, you have two 0 eigenvalues, right? Well, one is the constant function, one is a linear function. They're both 0. So you expect this equation. I actually never tried. Let's check these eigenvalues of this equation matrix. I hope it's not true. are there zeros? Should be, right? Should be zero argument. Well, maybe that. Okay, so I'll take it back. The determinant argument is still good. So well, okay. Then I should, because these numbers are pretty large. I'll show you again if I do the correct differentiation matrix, then the determinant will be even larger. This is just a numerical rounding off error. You apply so many large numbers and subtractants and cancel that that is a numerical error. If you use high precision, I guarantee it will be zero. And also the eigenvalues of this the differentiation matrix itself, so the d-spec, the second order differentiation matrix, those must have zero eigenvalues.
Is this a numerical precision problem?
This is surprising. Zero eigenvalues, right? Well, I should have tried this at home. I'll figure it out later. Yeah.
Yeah, we have time in the afternoon.
Yeah. This is maybe numerical precision. Well, okay. Let me try one thing then. Okay, I can just put here instead of n, take numerical values, but take 100-digit precision. That we can easily do. So now everything is 100-digit precise. Okay, it all looks a little bigger, but that's okay.
Little tension.
Well, now we just added zeros to this, so no, something must have gone wrong constructing this differentiation matrix with high precision. But okay, maybe mathematics gets worse and worse, of course. Fair.
That's fine.
I'll show you how at least to solve this equation. So what of course we are going to do is, because these equations are supposed to be linearly dependent, we're just taking the first row and the last row, and we're going to change it with the equation we want it to be. So the value here, this is the value of y at -1, I think, and this is the value of 1. This one, we'll just put all ones and zeros over there, so that this one times this one, and now the source was all 0, but at this specific point we want to put, well, the boundary condition, I think, was 5 here and -1 here, something like that. So here we put this equation. So if you read this equation, this one times this one just says 1 times this one is this. So this value is equals to 5. And here we do the same thing, all zeros there, and then the last one over there to implement on this row the equation corresponding to these boundary conditions. How do you do this in Mathematica? It's basically these two lines. So we just take the first row, all its elements will be a table, which is 1 at the first element and 0 otherwise, and the other one is also all zeros except for the last one, that will be a 1. So then if you look at the equation matrix, it should look like, that's also not the hundreds digits, but just the normal one. Indeed, I changed the first row to be this one, and the last row, well, you believe me, that's probably correct. I put these source terms, 1 and -1, corresponding to the boundary conditions. Did I do this correct? 5 minus 5? 1 minus 1. Well, I guess I put a -1 at the source because that's how I solve my equation. I always do minus source, so that was why there was a minus. And now we have our function, and now we hope it works. This I checked at home, so okay. So now indeed we have some numbers, and the boundary conditions are satisfied. Well, obviously they are. We did it like that. But now, lo and behold, we have our analytic solution. This is the line previously saved in DL, and then the list plot of these points on the grid points, and it goes straight through. But it's actually a lot better than this. I mean here, okay, how do you see how accurate that is, right? Maybe it has a 1% error, then you would be very disappointed, I suppose. So what I do is I list plot here the function values minus the analytic solution evaluated on the grid points. And what you see, the function values minus the actual values, these are like 30, are 15-digit accurate. So you see with only the matrix inversion, very fast, 15 digits accuracy everywhere. So this is basically what I want you to construct for this other equation, and then compute the time derivative in this way. And you can use this for many different things. That's it, right? Well, good. Then, okay, yeah. Questions about this? How to solve this differential equation? And are you all convinced that it's very fast to get so many digits of precision? Alright. Then the last thing I wanted to show you. In 2 minutes, right? So that's okay. I mean, I didn't want to talk about my own. Well, okay, this is of course what we do, but
We'll deduce it from the coffee break, of course.
no, I don't want to do that. I'll just flash 3 slides of recent work I did using these type of methods. So so this is not a homogeneous case. It just it's slightly more complicated. Also first done actually in that sense by Larry and Paul, but in this we refine that a little bit perhaps. Is where we take, this is a real collision, which is still homogeneous in the transverse plane, but it's a real collision in the longitudinal direction. So instead of having just this one-dimensional problem in integrating an R, we have to do this for every point in this collision direction because there's some non-trivial dynamics happening. And we can also put in a non-trivial initial state, which you kind of understand. And the nice thing is we can understand it because what we put in here is actually some kind of, well, in this case a Gaussian energy density, which moves at the speed of light to the right, and this one moves at the speed of light to the left. And here we actually understand the complete functional dependence as a function of R, because we just want this thing to propagate in vacuum unperturbed. You don't want a nucleus which goes in vacuum to kind of decay or something like that, you just want it to go on. And those we can write down even analytically. And then there's no trick. Then they collide, these gravitational waves in AdS, and then there's all kinds of Einstein equations happening, which we then solve using this characteristic method, basically doing a lot of these differential equations I just showed you. Like for every point, we need to do this nested scheme of 5 of these differential equations for every time step. So you solve it like well, 1 million times perhaps. So well, it's just a do loop, of course. It's not so complicated. And what you then see, so here I just plot the energy density of the result of the CFT as a function of time, as a function of